From here, we get, of course, 2 less or equal p less or equal than 7, but also that I want to exclude p equal 11, then you get 11 plus 1 is 12, so that would give you n sigma equal to 2, or p equal, well, 17, 19 is not possible, 23. That would give you n sigma equal to 1. But to exclude them, we use a K3 argument. So in that case, if I do A11, this gives, well, I have then 2 A times singularities. And this gives, here I have 1 A22 singularity. Okay. But then from the first case, so 1 implies that you have 20 minus 2 curves, independent. 20 independent. Independent, I mean as classes in the H2. Independent minus 2 curves. In, well, let's say, why not? NS, where is my notation? Y, which is in H2SY, YZ. Okay. And so we have a lattice of signature 0, 20. Of signature 0, 20. But remember that the signature of H2 SZ is equal 319. So I cannot have it, so it's impossible. Okay, I have too many curves. And P equal to 23 is even worse because I get 22. So it's impossible. And so the case 2 is similar. So you cannot have so many minus 2 curve on a K3 surface would generate a too big a sublattice negative definite. So you have only that range of between 2 and 7. But there is, I know that there is some result because one can do, well, as I say, one can do a lot of things with automorphism, study symplectic, non-symplectic one, and then you can study, for example, in a positive characteristic. And I don't remember which is the characteristic, maybe 11. But in positive characteristic, for example, if I remember correctly, there was some work saying that 11 is also possible, for example. And, okay. So that was the proof. And what do you want to do? Well, the number of 6 points you just compute using that one. Okay, maybe some remark on that fact. Some remark. Again, sometimes I go back to just to give some result in the projective case or not. This is independent again if S is projective or not. So the result is true for S projective or not. Okay, that's also this last discussion does not depend on if the K3 is projective or not. So the signature of this lattice or like this, so there is no problem. And second remark, I show you that these are the possible cases, but of course one asks, does this case exist? And the answer is yes, so all cases are possible. Exist, so you have example where we have seen already example of order 2 and 3 yesterday using quartic. You can do also the order 5, but not the order 7, because you start having a lot of condition, and if you start again, you can try to guess which is which should be the action of your automorphism. But in that case, you get quartic that are always singular. So one should use other method to find example. And I don't know if I will have time to talk about that. Sorry. Automorphism of the K3. They have really on the K3 surface.
Yeah, but like
I want to find the example.
Yeah, then maybe we should find the automorphism of the lattice.
You can, yeah. If you are, okay, yes, it's a good question. You can do that in 2 ways. You use Torelli. You try to use Torelli and then say, okay, the K3 exists. Or, well, you can, at some point, you want to see geometrically what it is. That's true. And also Torelli, well, you have to think about that you really can define an isomorphism with the good properties. But I was just talking about the geometric case. And geometric case, for example, you can produce all examples by using elliptic fibrations. So I say elliptic fibrations. I really hope to tell you a bit about that because, well, elliptic K3 surfaces have a really rich geometry and are important, well, not only for automorphism, but in many situations. And you can really see how to produce automorphism of any of that kind. So, third remark, one can formulate a similar result for sigma acting symplectically. Order of sigma equal to n, so I mean not necessarily prime. So you can actually do a very similar study. The only thing where one should be a little bit careful is that well, here it's clear that you have AP minus 1 singularity because acting by a root of unity, if the order is P, you necessarily order a primitive P root of unity. But if the order is n, you can look at each point which is the order of the stabilizer. So one should be a bit careful when describing the quotients. But essentially, you do in a very similar way, and one can find the following. So one find, again, as I say, just give you an idea which is then the order and S and sigma. You write it down. So I write it down completely. So we have the following order: 2, 3, 4, 5, 6, 7 until 8, and the number of fixed points is 8, 6, 4, 4, 2, 3, 2. If I'm not wrong. Be something like that.
The order of the group or
the order of the automorphism. So just the order of the automorphism. Just they are taking only one automorphism. But even more, let me say something more about the works on Nikulin. So he started with prime order and then any order, and then he even classified so Nikulin for any is the order of sigma. But as I say here, be careful. So here are all A1 singularities, here A2. Here are not all A3, so it depends on the action at the fixed point. So Nikulin classified all finite abelian groups acting on a K3 surface. Symplectically, okay, G for the say 3. So instead of taking one automorphism, so I study once each alone somehow, but you can ask for which kind of group can you have. And in fact, he gave a list, and you have 14 possibilities. There are 14 possibilities. And let me write down so you can just have an idea what it is. Of course, you have the cyclic group coming from here. For n, well, forget about the identity. N equal, so let's, I don't want the identity. N equal to 2 up to 8. Then you have a product like Zm times Zm with m equal 3, 4, and 2, 3, 4. Then you have Z modulo 2Z times Z modulo TZ. T is equal 4 and 6. And then the last one, you have Z modulo 2Z to the power 3 and Z modulo 2Z to the power 4. And that's all. I hope I wrote 14 groups. Okay, so that's kind of simple. But yes, I have the abelian hypothesis. But even more so is one, this was around the 80, but then this classification was completed for all groups acting symplectically by so a bit later. Okay, Mukai and Gang. So 5. And actually, the classification, the method essentially is all like that. You study the singularity in the quotient, and then you start arguing to see with the property of the lattice of the H2 which kind of group you can have. So Mukai and Gang classify then all group. Finite, always finite, acting symplectically. On a Kähler surface. So this means also the non-abelian one. Okay. And actually, I should say the maximal group acting non-symplectically, because of course you can take always subgroup acting non-symplectically. And just to give you an idea, the maximum order. So the proofs are different, but the proof of Gang again use a bit of that ingredient, of this quotient. The maximum order possible, and I think there are more or less around 10 maximal group. Well, I say all groups because you can take, of course, also the subgroups, but they give the list of the maximum order. So the maximum order possible is G less or equal than 960. And this is actually is a Mathieu group, which is called M20. One of the sporadic group. And well, this is can be seen as the semi-direct product of A5, so the even permutation, nothing to do with the singularities. And semi-direct power is Z modulo 2Z to the power 4. So it is a big one, and actually, again, they give the list, and this is an effective list. I mean, they give also example of K3 with this an action, so just a constructive. And all the examples are constructed explicitly, so giving geometric construction of the K3. And before I give you an example of at least that one. So that one, let me just remark another thing, which is also important. So, sorry, here I was, sorry, I was saying that, but not writing that. Then we have this. Another remark before to give an example of which is the K3 having that automorphism group, that Kondo, this is always around the 80, 90. Yeah, this is a bit later, 99 even. 1999 show that if now, so we go one step further, if G is finite, G acting on SK3, so no, I put no hypothesis of G. So G is so some way called, it's a group which is mixed. You have symplectic automorphism and non-symplectic one. Of course, it's not purely non-symplectic because we have seen it's cyclic and we have a higher order. So any finite group of automorphism acting on K3, then the order of G is less or equal to 384. And well, the proof he did was uses a lot of lattice theory and isometry on lattices. And we have an exact sequence. That's why I wrote down. Well, the exact sequence I was working before. Maybe to not confuse you, let me call H, sorry. Just to, because I call G that one, so I want just to change the name. So we have H here. Then you have Z modulo 4Z. Somehow this is a purely non-symplectic part that you have in H. And the kernel of this is G. If I'm not wrong, yes.
This is in place the maximal one?
So, yes, sorry. Sorry, yes, I say all of them. Thank you. Yes, thank you. Of course. Yes, that's true. You're right. Because 4 times 960 is 3,840. Sorry. So that one. And so you see that G is that group. So it's our M20 that acts symplectically. And so H is an extension by Z modulo 4Z of that group. Okay, and then which is the K3 surface? Well, we will see a bit, maybe in a minute, a bit later, that having automorphisms somehow give condition to your K3. Well, we have seen already that if you take a generic one, it has no automorphism. And if you put automorphism of higher order or bigger group, this push to have a high Picard number. So for example, in that case, somehow it's not surprising that the example is a K3 surface with Picard number 20. Then, so Grover, Kondo was showing that there is a unique isomorphism, K3 surface S with the action of this H of this group. And this is the Kummer surface. Well, it's nice because Kummer surface, you know, already has tend already to have high Picard number because you have a lot of curves. But this even more is a Kummer surface to the product of 2 elliptic curves. And when I write EI is the elliptic curve with complex multiplication by E equal divided by 3. So it is y square equal x3 plus x. Okay, it's an elliptic curve with complex multiplication, so a special one. You know, on a K3, on an elliptic curve, you have complex multiplication of order 2, any of them, 3, 4, or 6. Okay, so that's 4. And this is equation. So it acts by multiplication by I here and minus x here. So that one. And of course, this is a torus, so you can take the Kummer surface. But in that case, one can show that rho of S, which is the rank of peak S, is the maximum possible. Again, the fact that there is only one tells us that you cannot move very much. So 20 means that your moduli space is 0-dimensional. So it's not a reason, but well, a lot of hint that everything is correct. So that this is also an example of your, actually the only one, of the OK3 surface with such a symplectic action, this Kummer surface. And I mean, this is a very beautiful Kummer surface. So I give you also an equation. I like to give you equation. So an equation for that one. So again, S is abstract, but you study the lattice. So S can be embedded in P3 with the equation. So we recognize a surface that we had several times. But not exactly that one. You need something just a bit, somehow a deformation of that. 12, 0, x3, equal to 0. There are different ways actually to find this equation. Sometimes one way to study this kind of problem, so you can identify this group. So this is a reflection group of complex reflections. You start computing invariant by the action of the group, and then relation between the invariants can give you then the equations. So somehow. So that's a very, very nice one.
Which divisor will be embed?
Sorry?
Which divisor will be embed?
Well, it's a divisor of square 4. Okay, so I don't know. This is a smooth one, so it's a divisor. I don't know exactly how it looks like. Your Kummer lattice is big, you know. You have to find 20 generators and then write down the class with a square 4. So that's big. And then one can show that in your Picard lattice, which is need a bit of work, of course. If you want to do from point of view of lattice 0, you have to show that you have an ample divisor like this, or square 4, that you can make in P3, and then you can find the equation. But this is a smooth one, so this means that your divisor meets somehow the curves that come from the node and embeds your curves. I don't know here how, maybe lines or conics on this equation. But it's not the way how Kondo and Mukai find the equation. They find more the equation studying what are invariant polynomial by the action of this group. So I mean, it is actually it's very difficult even when you give the embedding of a K3 in some projective space to find explicit equation. So that's you know that it leaves some space, but how look the explicit equation? This is not trivial at all in general. Yeah.
This is it. Am I correct? To just find the group fixing this polarization, and after taking invariant, somehow find how it acts on the linear system, and after taking invariant polynomial.
You should find invariant polynomial. It depends also, I mean, the problem is that you cannot always realize your automorphism as automorphism coming from the projective space.
Of course, I mean,
not always, yeah. You need, but there are several automorphisms, for example, on quartics, and I guess here too. Yes, here too. There is at least one that does not come from the projective space, for example. And then these are difficult to handle because you don't know how to work with them. So that, but for example, in this case, if actually something I'm working on, so is that if you divided this by 2, you find a complex reflection groups, and all the reflection can be realized by automorphism coming from P3. So that's helped very much in finding kind of the equation, for example. But as I said, it's for quartic and the only surface in P3 where you can have automorphism not coming from the projective space. So that's why sometimes not. So it's not clear how to handle to do the equation. Okay, so let's go back now to general theory. So. Yeah.
So can we, from a group, can we figure out the dimension of the moduli space at least, or something like that? Did I miss something?
Yeah, that's a good question. Yes, yes. When you have some, let's say, symplectic or non-symplectic, yes, there is a way to construct the moduli space and compute the number of moduli. Okay. Yeah, I'm going to talk about, yes, right. It's a good question. That's nice. So let me talk about two important sublattices. So again, come into play some lattice theory. Okay, we have an automorphism. Again, this you can again forget if it is symplectic or not. Acting on SK3, then one can consider the action of sigma on the H2 sigma star. So I take the cycle, so the X in H2 SZ, such that sigma star X equal to X. So this is what is called the invariant lattice, for example. And of course, when you have the invariant lattice, you can consider also the orthogonal complement of that. So it is a sublattice of the H2, and let's take now the orthogonal complement. So you have then H2 SZ sigma star per, which are the cycle. Let's say I don't know y in H2 SZ. Such that yx equals 0 for an x in the invariant lattice. And well, this is called the invariant lattice. I don't like, sometimes people call anti-invariant. I don't like that, so I want to do it more for evolution. Let's say just orthogonal complement. To the invariant lattice. I will just say that. Does not matter for the moment. Just take any automorphism, you can define it. Yeah. Does not matter. Okay, one important thing. So now you have to consider it symplectic, or not even for the moment, not at all. We can think about the following thing. So you see here. So sigma star acts with eigenvalue 1 on all the elements. Okay, for all the point in that invariant lattice, sigma star of x is equal to x. But then sigma star cannot act. So the only thing is always finite order. Okay, let me assume all this however, always, cannot act with eigenvalue 1 on this orthogonal complement. Okay, because one can show, in fact, that one can show that H2 SZ sigma star intersect with the orthogonal complement is equal to 0. So one can show that if this lattice is non-degenerate, we have this is all non-degenerate, so the intersection is 0. So you cannot have, if you have something with eigenvalue 1 is a invariant lattice, but surely not here inside. So this means that if you take sigma of prime order, for example, so if you want to assume that the order of sigma is equal to p prime, then the rank of the orthogonal complement is equal to m times p minus 1. Because, so this means that the orthogonal complement, well, I will act, if I look on C, by root of unity, but any root has the same multiplicity, because everything given over Z. So that's why I have m times p minus 1, where here I said it's important, however, that I made the order of sigma equal to p. And let's now compute m. So now I go back again to the symplectic case. I think maybe we need that. Well, let's assume to be the safe side. First, assume also symplectic, even if I'm not sure. Sometimes in some computation, maybe I will not even need that. So we want to compute m. Because in fact, computing this space and the dimension will be quite useful then when we study moduli. So let's compute m. So to do that, we use the topological Lefschetz again. Or even better, it's important for moduli, but this tells you also some information about the size of the Picard group. Okay, so let's compute that and then we'll show you something. Use again topological Lefschetz. We use holomorphic Lefschetz, so now I'm using topological Lefschetz. So this means the following, that I have the key of the fixed locus, which I know, okay, I use symplectic, so I'm in the symplectic case, so this is a number of fixed points. On the other hand, so the key top can be expressed in the following way, the sum e equal to 0 to 4 minus 1 to the power I, the trace of sigma star on hi SR. Okay. So in that case, well, let me just really forget the odd cohomology because I don't have it for a K3. For the H4 and H0, it's 1. So it is 2 plus the trace of sigma star. Okay, since I'm looking on R, so I can split on the, looking the trace on the invariant lattice and on the orthogonal complement. Sigma star of sigma star on the orthogonal complement. and this is the following. This is eigenvalue 1, so I just take the rank, which is equal to 22 minus that one. Okay, this is just the rank of the lattice because I have eigenvalue 1, is what I say that. Plus, well, I say in the orthogonal complement, this is, I have primitive root of unity, each of multiplicity m. Okay, and recall that when I do the sum of the primitive root of unity, this is equal to minus 1. So this is minus m times p minus 1. Sorry, m. Why I say p minus 1? P minus 1, you don't need it. Of course, these are the root. So this, since you consider the sum of primitive root of unity, p minus 1, theta p is equal minus 1. Okay, yes, each root has multiplicity m, and then you take the sum. So this gives you in total the following. So we get, again, doing some computation. We know, also that n sigma was 24 divided p minus 1. And actually, if you do the computation, you get the same thing for m. So give you m equal 24 divided p minus 1 in all your cases, depending on the order of p. So if you want to look at a table, just resuming in the table, because this is quite important. So we had p is the order, and sigma the number of fixed point, and I put the rank of this orthogonal complement. I mean, you will see in a minute why I compute, why is important, why I compute that. So we have two, let's say prime number, 3, 5, and 7. We had 8, 6, 4, and 3, and this is the same. So let's now show, what I wanted to show is that this orthogonal complement is contained in the Néron-Severi group. That's why it tells you something about the size of the Néron-Severi group that you need when you want to have automorphisms. If you remember, when I give you the proof, remember saying that generically there is no automorphism. At some point I was saying, okay, let me study symplectic and non-symplectic one. And in the symplectic case, I must have at least 8. Actually, come exactly from here, from that one. So let's compute that. So assume, moreover, that S is projective, so that we go back to our situation. Even if we don't need. Well, you can do that. Assume S is projective. And I want to complete my table then with the rank of the Néron-Severi group. Bigger or equal than what? Well, I have already one. I have it because it's projective. But let's look at the following computation. Let V in TS, which you remember it was the complemental orthogonal complement. Sorry, I switched to Néron-Severi group or Picard group. It's always the same. Okay, for K3, the Néron-Severi group. Perp in H2. And let's apply the automorphism. So consider the scalar product, not the scalar product, sorry, the product with the bilinear form of omega S. Then we know that sigma is an automorphism. So this means that this is a sigma star V, sigma star omega S. Okay, so this means it's symplectic. So this means that this is equal to omega S. So this is V omega s. So one thing that one need now is the following, maybe. Maybe not, I should not do that way. Yes, maybe I should do in that way. Sorry, not taking in that one, but sorry, I started not in the good way. That one. We don't know anything about the transcendental lattice. So let's take it in that way. So you know that this is not V. Okay. So this tells us that sigma star V minus V times omega s is equal to 0. So this means that this difference is the orthogonal complement. Omega s perp in H2SZ. Okay. But if you remember at some point when I was describing the Néron-Severi group, this is another description of the Néron-Severi group. Okay, so I'm just thinking because yes, and what I wanted to say, I don't see anymore how, sorry, I was getting in trouble here. So I don't know. I just wanted to say that this is this must be equal to 0. Well, okay. So let me. I don't know. I wrote something wrong, and I don't see immediately how to correct that. So let me forget about that, and just maybe think about it. Just I formulate what I wanted to say without giving the proof because I cannot find any more the computation. But it's a computation like this, but I cannot find again the direction. So one can show, let's see, that way. That you take the orthogonal complement of the invariant lattice. So that's perp. This is contained in the Néron-Severi group. So that's why some computation is like this, but well, anyhow. And the transcendental lattice, TS, which is NS S perp in H2SZ. Well, this is contained in the invariant lattice. Yeah, sorry. It's a computation that I did. Somehow I started in the wrong direction and could not go out. But somehow this is something that one expects because if you look here, so if you look at here inside, I mean, the period live here in the transcendental lattice. And you know that on the period, the action is the identity. So it's somehow one expects that you are here inside. And so that's actually what happened. So we see two things from this, this fact. So we get two things. So the first factor is that the rank of the Néron-Severi group is bigger or equal than the rank of that lattice. Sigma star perp. And one need also one fact that Nikulin showed, that this lattice is a negative definite. is negative definite, and you have projective. So in fact, the rank of your Néron severity group, there is several ways to actually say that, is the rank of that plus 1. So is equal, exactly is equal to 9. So your ample class cannot be contained here. But I mean, this is actually quite clear, because if you have something that is projective, so you put in some space, and you take the ample class, and you take the average of the ample class, you get something invariant, which is still algebraic. And so it lives, is invariant, it lives here, so surely does not live here. So this is not, actually 9 if S is projective, then 7, then 5, and here we have 4. Okay, so you see that each time you're, oh, sorry, writing something wrong. Of course, I forgot to multiply by p minus 1, but here is 9, that's correct. But anytime I have to multiply by p minus 1, so it's 13, 17, and 19, sorry. Well, I'm glad that. So you see what is interesting here, that anytime you have that Picard number get bigger. And that is what I was saying at the beginning, that having automorphism is something very special for academic K3. So that tell you that the Picard number must be high, otherwise you have nothing in some sense. Okay. Okay, maybe let me give some examples more. So here maybe. So the following example, actually, we discussed this this yesterday. But let me recall just, well, I don't have very much time, so maybe I have to do a choice what I'm going to tell you. Maybe, well, let's recall some example with the order 3, symplectic automorphism of order 3. Again, we've seen yesterday, this is x0, x1, x2, x3. Let's go to x0, x1, theta x2, theta square x3. And so theta is a third root of unity. And we consider the invariant polynomial for this of degree 4. Okay, so degree 4 invariant polynomial we've seen yesterday. Well, we computed yesterday, so this is Q4, x0, x1. Then you take x2 square, x3 square, something of degree 2 in x0, x1, plus something linear in x0, x1, plus x3 to the power 3, something linear in x0, x1, and alpha, this product. So if you look at the equation of a generic quartic, which is invariant for that automorphism, looks something like this. So it's kind of this equation. As usual, you can check that the action is symplectic, as we did yesterday. It was exactly like what we did. So we have this invariant quartic. Again, we can show the action is symplectic. And one can compute moduli. So we did it already, the exercise several times, how to do that. We compute parameters, and then you must take away the automorphism coming from P3 that commute with that. And one can see that one can find seven moduli. If you look at your table there, take the order 3, you really see that, so you have 13. So if you do 20 minus 30, that is 7. And in fact, so generically, one can show that the moduli space of K3 surfaces with the symplectic automorphism of order 3 depends on has dimension 7. So the reason is exactly actually what is written there, that generically your Néron-Severi group generically is equal to, let's say it that way. So generically, this is the explication, so I will finish. The Néron-Severi group of S, in that case, is equal to ZL plus what I call, sorry for the notation, is not, I should not really use that. So let's say is equal to that lattice or it is another lattice of it. Lattice of finite index of it. So one can describe it completely. So this is a Néron-Severi group. And you do the construction of the modular space as we did. So this means that period moves in the orthogonal complement, tensorized by C. And then you can see that, that in that case, you exactly have this, well, the orthogonal complement is 13. So you go to 22, okay, which is 9. But then is projective, so give you 1 dimension more. And then you have the equation of the quadric, which is another dimension more. So that's why you find again these 7 moduli. And actually, this is more or less the way how you construct the moduli space. That's work in any case. So that's, for example, for order 5, you have only a 3-dimensional family. And for order 7, 1-dimensional family. One remark. Second remark, of course, it depends always on the polarization that you put on here. So you can have L square equal to 4 for quartic, but then L square equal to 6 if you find other projective model and so on, so that you can describe this, this moduli space. And then I think, yes, that unfortunately I cannot talk about, as I said, about elliptic A3. One maybe last remark, since I have to finish here. One can, for the order 3, describe this lattice, because this lattice does not depend on the, somehow one can show, does not depend on the K3 and the automorphism that you've chosen. It is always the same for K3. And for the order 3, is something called the Coxeter-Todd lattice. And say the funny or interesting thing is that this lattice is one, there is the problem of sphere packing in any dimension, how you can put balls so that they are the most dense in the space. And this is the lattice, so the lattice points give the highest density possible in dimension 12. That's called the Coxeter-Todd lattice. And in other cases also we find some lattice giving high density. I don't know the reason, but somehow it's kind of interesting. How do you find this lattice is a completely different context, which is the context of K3 surfaces. Okay, I stop here.